Welcome. I want to talk about isospectral deformations of the Dirac matrix. Something I observed last week is that if you take a Dirac matrix which appears here in finite geometry, like for a simplicial complex or a delta set or a graph, that you can deform that using the QR decomposition. Every matrix can be deformed by QR decomposition. You just write it as the QR and then you flip the Q and R. So then you get the RQ. And because the Q is orthogonal, this is isospectral. It's a numerical method to diagonalize a matrix. Doesn't always work. And actually just in this case of Dirac matrices, we can, for example, get to fixed points pretty fast. So in this case, we get to a fixed point after one step already. But it's an interesting thing, and it's a theme I have pursued for many, many years. Actually, when I was starting doing research as a graduate student, I worked on the Toda flow deformation of Jacobi matrices. I did then also deformations of random Jacobi matrices which appear as Hessians of variational problems in also infinite dimensions, like when you look at the twist map. And I was hoping that the deformation would kind of give us some information about this, motivated by the Witten deformation, which is also a deformation of the exterior derivative. The Witten deformation is not isospectral, but it preserves the cohomology, the kernel of D remains the same. And so this didn't work out here as a tool for ergodic theory, but it's an interesting topic, and I got into here some interesting mathematics also. The Lux deformation of Jacobi matrices produces translations on the Picard group, and which is associated to a hyperelliptic curve. So there's a lot of algebraic geometry involved here. So the explicit linearization of this integrable flow, all the eigenvalues are invariant, right? It's integrable. There are many, many integrals. And here in this case, this is also isospectral, so all the eigenvalues are invariant. So this must be considered an integrable system. So in this case, it would be actually interesting to see what happens also with algebraic geometry, what happens with the dynamics. I don't yet know here what is the general picture. So the general question is what happens in the long term for a general system. But for me, it's just important is that this is a symmetry. So symmetries are very important in mathematics and physics. So you have this covariance principle, for example, in general relativity, the general covariance principle there, where you have diffeomorphisms. Now in finite geometry, you have very few symmetries coming from, deformations. The automorphism group of a, general space is small. So in this case, we have a triangle. If a triangle, of course, you have rotation, so you have a relatively large symmetry group. It's a finite group, but if you take only kind of just change a couple of things, then add a couple of edges to that graph, so a general random graph has no symmetry. So there is no deformation in that case. So that's a bummer, right? Because you want to have symmetries. You want to have these in finite geometries, you want to have symmetries. But fortunately, we have quantum mechanics, meaning that we have a Hilbert space, which is L2G. So this is kind of just produces the basis of a finite Hilbert space. This is a matrix in that, an operator on that self-adjoint operator, and this is the R was given as dimension, and we want to have this compatible in the sense that the D maps K forms, which are just functions on Gn, to K+1 forms, which are functions on Gn+1. So you want to have this. This is called a cochain complex. It's also a category. What is cochain complexes form a category, and the morphisms are chain homotopies. So in a fancy way, we can say that this QR decomposition produces a chain homotopy of the finite geometry, and it's not trivial. Unlike kind of if you make deformations of the wave flow, if you let wave dynamics move on a finite geometry, that's already quite interesting, because we can for example, kind of get kind of continuum analogs of what happens with the deformation, what happens with motion on the finite geometry, which is not possible in the discrete, right? It's kind of hard to say, but in a wave dynamics, it's just easy to describe, and it's just given by, you know, linear flow. But this linear flow, if you take the, you know, the d as the generator of the translation of the space, then this is of course not changing the d, so it doesn't change the geometry. So I was very excited when I, a couple of years ago, almost 10 years ago, actually 10 years ago now, looked at this isospectral deformation. I was excited because it is a deformation which also produces a bt. So you have these dt, which are kind of non-isospectral, like the Witten case, but still the cohomology stays the same, the kernel stays the same, so you have the same cohomology. So you have a deformation of the geometry, but because they are becoming smaller, actually exponentially smaller, you have an exponential inflation by this gone picture, which is a very simple way to kind of bring a metric structure on a, you know, on this finite, also finite geometries. So Gon called this spectral triple. You have a Hilbert space, which is L2G, you have the Dirac matrix, and then you have an algebra, von Neumann algebra, which can also be non-commutative. So in this case, could, for example, take L infinity G, but you can also look at non-commutative. I think that's the non-commutative geometry picture. And we have also a topology here. That's kind of something to add. We have an algebra, right? We can look at the chains. They kind of, you can take these disjoint unions and we can add them. Look at this as a monoid, produce a group. This gives the chains, and then also have the multiplication, which is the Cartesian product. And so we have a ring structure, which is also nice. So this finite geometry produces a tremendous amount of ways to look at things, and this is another aspect where kind of integrable systems come in. Now in that case, I also was looking at QR decomposition here in the random case, where it's a little bit kind of problematic. In the infinite dimensional case, there are the shift matrix, right, is also right, is also upper triangular. So the distinguishing between Q and R is no more so clear in the infinite dimensional case. But if you look at finite dimensional cases, this is an observation from 82 by science, that you can actually integrate also this flow here using QR decomposition. Now, and that's actually something I don't know yet, but I hope that one can also just integrate this using a QR decomposition. So the idea would then be to do the same thing than Sims did. You just take the e to the TL, which is kind of this heat wave operator. If you look at this as a complex number, it doesn't, and then you look at this QT RT and hope that this actually, the DT is actually the solution. I did not try that yet, but I will certainly look at this. That's it for today.